to this point in the course, we have mostly focused on gaseous systems that were in fact ideal gases. And one of the reasons for that is that the equation of state for an ideal gas is particularly simple. In other words, we can just simply write down P times the molar volume is just equal to RT. And it's easy to manipulate this. It's easy to solve for any of these physical properties in terms of the others. So it makes for a very convenient way to look at physical systems and understand something basic about the thermodynamics. All right. Now, this is okay if we're only dealing with very dilute samples, because they will all more or less be well satisfied by the ideal gas equation of state. But in fact, real substances don't do that. And so what I want to do is start talking a little bit about what non-ideal gases are like and what contributes to that non-ideality. Now, one of the things I want to do is also talk about this molar volume, okay, which we really define essentially as the total volume divided by the number of moles. I'm also going to sort of expand upon this a little bit to connect this to another quantity called the number density. Now, the number density is the number of molecules divided by the volume. Or in other words, we could relate it to this molar volume. As you can see, it would be something like 1 over the molar volume. So the molar volume might look like 1 over rho, but we'd have to correct for the fact that this involves the number of molecules and the molar volume involves the number of moles. But converting from number of molecules to number of moles should be a fairly simple procedure. So why do we need to change something like the volume? Why do we need to change the pressure? Well, there are two qualities or two properties that would lead to ideal gas behavior, and they are the pressure and the volume. The temperature is pretty much just affecting how fast molecules move. All right, so what happens when we start thinking about more deeply about the pressure and the volume in these cases? Well, first of all, we find that molecules themselves have a finite molecular volume. In other words, molecules actually take up space. Now, in our ideal gas model, we treat them as point particles. We also know that molecules have forces that they exert on each other, and we'll call these intermolecular forces. And these intermolecular forces actually have an effect on the pressure. So let's look at what each of these does. In the case of the finite volume that molecules have, how does that affect them? Well, it means that the volume of the gas, that is to say, the volume that actually is evident for the gas, is actually greater than the volume that we might have had for an ideal gas. Because the ideal gas has point particles that don't take up any volume, but if now we add the volume of those gas particles, the actual volume actually must be greater than what we perceive for the ideal volume. All right, it turns out that this is a short-range effect. That is to say, the size of a molecule only matters if you have two molecules that are close together. So it won't matter if we've got a bunch of large molecules if all of them are so far apart that they don't really perceive that size. All right, now what about for intermolecular forces? What effect does that have? Well, these are largely attractive forces. So I want you to imagine what that means for a molecule. If the molecules are sticking together a little bit, that means they're not colliding with the walls of their container as well. They're not exerting as much force per unit area. So what this does is it has the effect of reducing the effective pressure. And because these forces are are attractive, they tend to be long-range forces. So they're going to have an effect at longer range, which it means that even dilute ones might show some effects for this attractiveness. Okay, so the bottom line here is that the ideal gas really is good only if we have a very dilute sample. Okay, which means that we have either a large volume, or I'll say a large molar volume, or a low pressure. All right, so this is the domain in which these things work. Now, what effect does temperature have? All right, well, let's look at two ranges, okay? I'm going to consider low temperature. What happens at low temperature? Well, the molecules aren't moving as fast. So if they're not moving as fast, that means they're going to feel those attractive forces, between each other. So the attractive forces are dominant. So we're mostly going to see the effect on pressure, as I indicated up here. So what we're going to see basically is that we see a reduction in the pressure under this case. If we're at high temperature, what happens then? Well, the molecules are moving faster, and so the attractive forces don't do as much. They may deflect the particles a little bit, but they don't have as big an effect. And what tends to happen is the repulsive forces become then the more dominant one. That is to say, we're going to see more of the exaggeration of the volume in the case when we have higher T. All right, well, what we need to do is figure out a way that we can visualize all of this. Now, one of the manifestations that one finds for a non-ideal gas is that there are certain things it can do that an ideal gas cannot. Now, let me describe what I mean by looking at a PV diagram and some isotherms on that PV diagram. All right, so here's a PV diagram, and we know that when we're at high pressure and high volume, we have isotherms that look more or less like this. Okay, these are the sort of isotherms that we've been drawing all along. So these are in a range that I would call the ideal gas range for these kinds of systems. All right, but I'm going to change color here so that I can emphasize what happens in the opposite of that range. What if we're at very low pressure and we're way out here and we're coming up to some point here? It turns out that at that pressure, as we continue to reduce the volume, it will jump over and reach a point here. And from this point over here, it actually goes up very steeply in pressure. So something happened in here. I'll put a little question mark there. All right, this will continue for several of these isotherms that come up. There's a gap, and then they resume over on the other side, and they go up very steeply on this side. Now, the magic of all of this is that there is a special isotherm in the middle here. So what's happening between these two ranges? Well, we see at first that these isotherms come down, they kind of have a little distortion in their curve, but they continue to proceed more or less like the isotherms of an ideal gas. But eventually they will come down. There will be a special isotherm that comes down and it reaches a zero slope. That is to say, it's perfectly level in slope here. It turns out its second derivative is also zero at that point. And then it continues on down. And below this point, at any temperature that's below this, we'll have this sort of gap behavior that occurs here. So, in fact, what can happen is we can map out a region here in which that gap occurs. And in this region, that's where something different is happening. Now, we get a clue as to what that something different is if we look at what's happening over on this low volume end of this PV diagram. What's happening over here is that we now have a liquid. So in other words, the ideal gas up here has properties now that allow it to condense. And this is what happens in real gases, that is to say non-ideal gases, is they can make this transition from being more or less ideal over in the upper right to essentially being not a gas anymore at all. They're a liquid now, which is still a fluid state, but it's a different sort of fluid state. So what we're going to try to understand in this module is what's happening in here. Now, in effect, what's happening here is that we can draw horizontal lines across here that connect these two things, because this region here is a liquid vapor coexistence region, which is to say, in this region of this PV diagram, that all of this area in here, we have both liquid and vapor, and they're in equilibrium with one another. All right, the fact that we're drawing a horizontal line here is really just a construct for us so that we can connect up the two parts of the isotherms that exist over here, which look very gaseous, and the isotherms over here that are very much in a liquid state. All right, how else can we think about this? Well, let me introduce a new quantity that will help us to visualize what's going on in these cases. And that new quantity is something called the compressibility factor. So let me spell that out for you. Compressibility factor. And that compressibility factor has actually a very simple definition. Something comes out of the ideal gas equation of state. Unfortunately, we use the letter Z for this, so don't confuse it with the system partition function. I'm sorry that we ran out of letters, but this one is also called Z, but it's defined as the pressure times the molar volume divided by RT. Okay, well, wow, that's a pretty familiar sort of looking thing. If we had an ideal gas, so I'll just say for an ideal gas, then this compressibility factor equals 1, right? Because P times the molar volume is equal to RT. So let's draw out a picture of what this compressibility factor might look like. So I'm going to draw a big graph over here. And now I'm going to have 1 sitting here. This is the compressibility factor. What am I going to draw it as a function of? Well, let's see how it varies with pressure. So I'm going to let pressure basically elevate from 0 pressure up to high pressure. So we know that all of these substances that we deal with near 0 pressure, that corresponds to a dilute sample, okay, low pressure. So at a low pressure, we know that those samples are going to be right around here. This is where the ideal gas sits in this diagram. All right, if we were to have an ideal gas, it would follow this dashed line all the way across the diagram. So I'll label that over here also. This is the ideal gas thing that we can compare against. Now, what happens to most real gases, though? What do they look like on this? And this pressure, by the way, goes up to hundreds, I'll say hundreds of bar. Okay, I'm not going to put an actual scale on that, but we're talking a very high pressure. So one bar is going to be way down here near this point. All right, but at higher pressures, what do samples do? Well, it turns out that most samples actually decrease in their compressibility factor. They reach a minimum point, and then they come up and they cross this ideal gas line, but they continue going above it. So what's going on here? All right, what is happening in this thing? At this point, it fortuitously looks like an ideal gas, but it's really just a cancellation of opposing factors. All right, what's happening here is that at these high pressures, this is a place where the attractive forces are dominant. All right, and this temperature would be, I would say, a low temperature for this one that I've drawn here. All right, but at that low temperature, we have the dominance of attractive forces, which means that it is reducing the pressure relative to what the ideal gas would have. That's why it's coming down this way. As we increase the pressure, though, what happens is that we're now getting into a realm where the repulsive forces are becoming more dominant, and it's exaggerating V. So you can see that the molar volume and the pressure are multiplying by one another here. So the point at which they changes in them are exactly balancing is where we reach this point that we cross the ideal gas line. But when the molar volume now gets exaggerated more than the pressure is reduced, that's when we see this curve rise above that. Now what happens as we change the temperature? Well, let me draw that in different colors. As we gradually raise the temperature, we would see these curves flatten out a little bit. And eventually we might have a curve that just stays up above here and goes over here. All right, so we'll see a wide range of behaviors, but this is basically increasing temperature. Out here, it's going down. So you can imagine at a really high temperature where all the gases are really buzzing around a lot, it might look a lot like an ideal gas again, because at that point the attractive forces are not really playing any effect, and the finite volume is also probably not having as great an effect. All right, now a lot of what people try to do is to understand why these ideal gases work this way. I think the finite volume we can understand, but the attractive forces require a little bit more explanation. Now, what I want to do is draw another picture for you. And I want to draw a picture for you of what these things look like as the distance between, say, two molecules in a gas might look like. Now, along this axis, I'm going to draw an energy. So I want to color for you what an ideal gas looks like on this picture. Okay, in an ideal gas, if this is sort of zero energy, the gases have zero volume. So that means we can get down infinitely close, and they can't get any closer than zero. So this is like a hard wall for an ideal gas. There's no attractive force between ideal gas particles, so zero energy is as low as it goes here too. So we would also have, if you will, a kind of a barrier here along this lower border. How do real gases differ from this? Well, it turns out they don't have a zero volume. They have a finite volume. So they come down here, and let's call this number sigma. You'll see why in just a moment. I'm going to call this value sigma. That represents, if you will, some sort of hard sphere radius. So that's basically as close as molecules can get. Now it turns out they don't just stop there and go straight across. They actually come down, and there's a little bit of an attractive well. And then they eventually come out here, and as they're infinitely far apart, they would have no more attraction anymore. So this curve, and I've drawn this curve before in talking about covalent bonds, but this curve is indicative of the intermolecular attraction that molecules feel toward one another. And this piece out here actually has a functional form that goes as 1 over r raised to the 6th power. And that's something that is a result of quantum mechanics. So one can actually do a detailed calculation. We're not going to do that here, and I'm not even going to bother you with the details. But this long-range force actually goes as 1 over the distance between the molecules raised to the 6th power. Now, one consequence of this is that there's a very good model for these forces called the Lennard-Jones model. Lennard-Jones. And it's not Leonard as spelled like a first name, it's L-E-N-N-A-R-D. And that curve, this curve that I've drawn in the Lennard-Jones potential, has the following functional form. It's equal to 4 times epsilon times 2 parts that depend upon r. There's a sigma over r to the 12th minus a sigma over r to the 6th. Now what does this mean? Well, this piece out here, this epsilon, is really the depth of this well. So it tells you roughly the strength of those intermolecular forces. This thing here is like we're essentially scaling the distance between particles based on the hard sphere radius. Okay, but it's 1 over r to the 12th, and this is a positive number. So what this is doing is this is basically building this part of this potential, and this part is building this part of the potential. And in here, we have sort of a balance between these two different kinds of forces. All right, we're not going to do anything calculational with this. That doesn't mean you should just forget it. What I'd like for you to do is remember there is such a thing as a Lennard-Jones potential, that it is a commonly used way of treating and modeling these intermolecular forces, and that it does an extremely good job, really, of modeling and of reproducing a lot of the various properties that we see in non-ideal gases.